Good evening, everyone. I welcome you all to the live session of NPTEL course, Non-Conventional Energy Resources. The course instructor for this course is Professor Pratap Haridos sir from IIT Madras, and I am the TA for this course, Amit Kumar Sharma. So today we are taking the live session for week 4 course content. So in this live session, I will discuss the week 4 course content and briefly revise all the aspects that were taught by the professor in the class. And I will also discuss some sample assignment questions with you. So those questions will be very helpful to you for your current assignments. And you can ask any doubt in between the class if you are having any doubts regarding the course and regarding any structure and regarding like questions and any patterns. Regarding any doubt for this course, you can ask me. The PPT and the recording of this live session will be provided to you. The course team will provide a link, a Google Drive link to you. So from that you can access the course material also. Okay, so let's begin with the live session of lesson 4 for the week 4 content. Okay. So in week 4 we have covered the black body radiation. Let me enter into the presenter mode. So in this week we have covered about the black body. Like what is the black body radiation in what is the black body, and let me just give me 1 minute to check my pen input. It's having some issue. Let me check. Just give me a moment. Okay, it's not working. I will click it. Okay. Okay. So black body radiation is thermal electromagnetic radiation within or surrounding a body in thermodynamic equilibrium with its environment emitted by a black body. So black body is basically an idealized opaque or non-reflective body. So black body is idealized opaque. Okay, so it will not transmit any rays from it, and it's non-reflective. It also not reflect. So basically, black body will absorb all the radiation. Okay, so black body radiation is the thermal electromagnetic radiation within or surrounding a body in thermodynamic equilibrium with its environment. It has a specific continuous spectrum of wavelength inversely related to intensity that depend only on the body's temperature, which is assumed for the sake of calculation theory to be uniform and constant. So uh, it's also depend on the temperature. Okay, so as the temperature increases, the radiation from that body will be increased. So it has a specific continuous spectrum of wavelengths which are inversely related to intensity that depend on body's temperature only. So basically the main thing that define the intensity of that black body radiation is the body's temperature. Okay, and when we do the calculation, we assume the temperature to be constant. So a perfectly insulated enclosure which is in thermal equilibrium internally contains black body radiation and will emit it through a hole made it in its wall, provided the hole is small enough to have a negligible effect upon the equilibrium. So this method was given by the Kirchhoff. So Kirchhoff developed a black body in 1859. We will discuss that in next slide. So basically, you can make a small enclosure that is perfectly insulated. Okay, so that is perfectly insulated and there is only a small opening. So and it is considered in thermal equilibrium. So 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 there is only one opening. So the radiation will coming through that one opening only. Okay, so the hole is small enough to have negligible effect on the equilibrium. Okay, so a black body at room temperature around 23 degree radiates mostly in the infrared spectrum, which cannot be perceived by the human eye, but can be sensed by some reptiles. So human eye cannot sense the black body temperature radiation at the room temperature, but some reptiles can sense it. As the object increases in temperature to about 500 degrees centigrade, the emission spectrum gets stronger and extended into the human visual range, and the object appears dull red. Okay, so if the temperature increases, it means the intensity of that black body radiation will increase. Okay, so now the intensity has increased, so that will appear in the visual range of wavelengths. We have covered the wavelength in our previous lesson. So if the temperature increase mean intensity has increased, so the wavelength will come under the human visual range and the object appears dull red. As its temperature increases further, it emits more and more orange, yellow, green, and blue light, and ultimately beyond violet or ultraviolet. So basically, as the energy increases, its wavelength will decrease and it will move through the visible spectrum to the ultraviolet spectrum. Okay, so temperature is playing a major role in black body radiation. So let's come to the next slide. I think you are able to see the pointer. If you are not able to see the pointer, please let me know. So here you can see that this is a enclosure. This is perfectly insulated. Okay, and there is a small opening here. Okay, this small opening. It's a very small opening. Okay. So as the temperature T of the body increases, intensity of the radiation from the body also increases. So it's depending on the radiation intensity depend on the temperature. Higher the temperature, lower its wavelength of the most intense part of the spectrum. So the temperature increases, lower is the wavelength of the most intense part of spectrum. That's why when the temperature increases, the intensity increases, and the emitted radiation will come into the range of visible, and if the further intensity increase, it will go in the ultraviolet range. And this is the standard. This is the statement from the Kirchhoff. Okay, so this is the statement of Kirchhoff law. It is for a body of any arbitrary material emitting and absorbing thermal electromagnetic radiation at every wavelength in thermodynamic equilibrium, the ratio of its emissive power to its dimensionless coefficient of absorption is equal to a universal function only of a radiative wavelength and temperature. That universal function describes the perfect black body emissive power. Okay, so this is the statement of Kirchhoff law. Okay, and this is the black body designed by the Kirchhoff law in 1859. So in simple words, you can say a black body is having the absorptivity, the absorptivity and reflectivity is equal for a black body. Okay, so the how much radiation it absorb, it will emit those radiation. So as the temperature T of the body increases, the intensity of the radiation from the body also increases. It is these are two major properties of a black body radiation. Okay, higher the temperature, lower is the wavelength of the most intense part of the spectrum. Okay, let's come to the next slide. So here we can see again, I think these have already covered in our last lesson, but let's revise it again. So you can see these are temperature, these 3000 Kelvin, 4000 and 5000 Kelvin. Okay, and these are three bands. This is UV, this is visible, and this is infrared. And the lower x-axis is showing the wavelength in micrometer, and the vertical or y-axis is showing the spectral radiance. So here you can observe that we are having three wavelength ranges. One is UV, second is visible, and third is infrared. And you can observe that when the temperature is increasing, this is 5000 degree Kelvin, is 4000, and this is 3000. Okay, so you can see the peak wavelength. Okay, so for 5000 Kelvin, the peak wavelength is lying in the visible wavelength zone. For 4000 Kelvin, the peak wavelength is lying in again visible zone, but slightly on the right side of the previous higher temperature. For, for 3000 Kelvin, this peak has again shifted towards the right. Okay, you can see here. This is the wavelength for 5000. This is for 4000. This is for 3000. So as the temperature is decreasing, the peak of wavelength is shifting towards the right. Okay. So, or if the temperature is increasing, the peak of the wavelength is shifting towards the left. That's why in the first slide we have covered that the black body radiation, the temperature is high, so we will be able to see those radiation. So we can see the, so you can see this is a visible range. Okay, this is the visible range. Okay, so this can we see if the radiation is in this range, we can see. And after that, the infrared radiation, and before visible, there is UV. Okay, so in this diagram also you can see that this is temperature T2 and the lower one is temperature T1. So the T2 is greater than T1, then the peak of the wavelength is shifting towards the right side. Okay, this is a very important consideration, that the peak of the wavelength will shift towards the right side when the temperature is decreasing. Now in this week we have also covered about the photoelectric effect. So the photoelectric effect is the effect in which electrons are ejected from the surface of a metal when light is incident on it. Okay, so the basically electrons are ejected from the surface of a metal when the light is incident on it. These ejected electrons are called photoelectrons. So in this diagram you can see that this is a metal surface. So metal surface is having some electrons. Okay, because metal is having some electrons in their band. So when the incident light will strike the metal surface, it will provide some energy to the metal, and it will emit. So after the electrons will ejected from this metal surface. Okay, so this ejected electrons called photoelectrons. Okay, now the emission of photoelectrons and the kinetic energy of ejected photoelectrons. So these electrons will also have some kinetic energy, because incident light is giving some energy to this metal surface, and due to that energy, the outer part, suppose the outer part of outer part electron, this particular metal, are ejecting and getting some kinetic energy. So the emission of photoelectrons and the kinetic energy of the ejected electrons is dependent on the frequency of the light that is incident on the metal surface. So the intensity, the kinetic energy of ejected electrons will depend on the frequency, and we know that frequency of the light will decide the energy. Okay, so we will see further. The photoelectric effect occurs because the electrons at the surface of metal tend to absorb energy from the incident light and use it to overcome the attractive force that bind them to the metallic nuclei. So initially the metal surface, all electrons are binded to the nucleus. Okay, they are having some bond energy, but when the incident light is impinging on the metal surface, so that light will provide some energy that nuclei. Okay, so by getting that energy, electron will break the bond and they will ejected from this particular metal surface. and they will have some kinetic energy due to energy given by the light. Okay. So the photoelectric effect is very simple. It occurs because the electrons at the surface of metal tend to absorb energy from the incident light and use it to overcome the attractive force that bind them to the metallic plate. So the particles of lights are some particles are hitting the metal surface, or some light is hitting the metal surface. They are having some energy. They are having some frequency. So those particles are called photons. Okay, so the energy held by the photon is related to the frequency of the light via Planck's equation. So E equals to h nu, and nu is equals to c upon lambda. Okay, so the light is having some particles, so that particles are giving energy to the metal, the electrons on this metal surface, and they are breaking the bond with their nuclei, and they are ejecting from that metal surface. So these particles of light are called photons. Okay, so the energy held by a photon is related to the frequency of the light via Planck's equation. So this is the Planck's equation given by the scientist Planck. It is E equals to h nu, and nu is c upon lambda. So where E denotes the energy of the photon. So E is denoting the photon energy. H is Planck's constant is very important. We will see the value in next slide. What is the value of Planck's constant? Okay, and the nu denotes the frequency of the light. So its nu is denoting the frequency of the light. C, and we can write, if we know the frequency directly, we can put directly h nu, and we are not having the frequency of light, then we can put c upon lambda. So c is the speed of light in vacuum. Okay, so electromagnetic waves considered to be travel at the speed of light in vacuum, and lambda is the wavelength of the light. Wavelength of the light. So you can write E is equals to h nu or h c upon lambda. So thus it can be understood that different frequencies of light carry photons of varying energies. Okay. So here you can see that in this slide we have seen that wavelength and spectral radiance are connected. Okay. If the wavelength is increasing, so up to a certain wavelength, the spectral radius increases, and after that, if you further increase the wavelength, the spectral radiance decreases. So wavelength is directly connected to the spectral radiance or energy. Okay, so it can be understood that different frequencies of light carry photons of varying energy. So we know this that because we are having various electromagnetic wave, we are having spectrum of various waves. Okay, spectrum of various waves. So they are having different wavelengths, so and different frequencies. So every frequency is associated with a particular wavelength, and that wavelength is associated with particular energy intensity. Okay, so based on that, the energy held by that photon will be vary. Okay, so because E is equals to h nu, and h nu and equals to h c upon lambda. So the energy of that photon is inversely proportional to the wavelength. So if the wavelength will increase, so if lambda will increase, it means the energy of photon will decrease. Okay, if lambda will decrease, energy of the photon will increase. Okay, so the energy of the photon will depend on the wavelength of that particular wave. For electromagnetic wave, for example, the frequency of blue light is greater than that of red light, because the wavelength of blue light is much shorter than wavelength of the red light. Okay, frequency of the blue light is greater than that of red light, therefore the energy held by photon of blue light will be greater than the energy held by the photon of red light. Okay. So the frequency is more means energy is more. Okay, because nu is directly indicating the frequency. So E is directly proportional to the frequency. So E increases when frequency nu will increase. Energy of photon will decrease when the frequency nu will decrease. So blue light is having more frequency. Okay. More frequency mean the shorter wavelength. Red light is having less frequency mean the longer wavelength. So the energy held by a photon of blue light will be greater than the energy held by the photon of red light. Now for the photoelectric effect to occur, the photons that are incident on the surface of metal must carry sufficient energy to overcome the attractive forces that bind the electrons to the nuclei of the metal. So as we know that metals is having some nuclei, and that nuclei is having some arrangement of proton, neutron, and electrons. Okay, so the electrons are binded in the binded to the nuclei. They are having some attractive forces there. So to break that attractive force, to break that bond, we require energy. And when sufficient energy is is strike that metal surface and provide the sufficient energy to the electrons so that they can break the attraction, they can break the bond between the attraction to nuclei, only then they can leave the metal surface. Okay, so for the photoelectric effect to occur, the photons that are incident on the surface of metal, so the photons that are incident on the surface of metal must carry sufficient energy to overcome the attractive forces. The minimum amount of energy required to remove an electron from the metal is called the threshold energy and is denoted by the symbol phi. It's very important. So there is some minimum amount of energy that is required. If you are having more energy, then it's okay. The electron will leave the metal surface and it's also have some kinetic energy with that. Okay. But there should be a minimum amount of energy required to remove the electron from the metal. Okay, that is called threshold energy, and we denote by the symbol phi. For a photon to possess energy equal to threshold energy, its frequency must be equal to threshold frequency, which is the minimum frequency of light required for the photoelectric effect to occur. So as in previous slide, we have already know that the energy depend on the frequency, energy depend on the wavelength. So energy of photon is directly proportional to the frequency, and energy of the photon is inversely proportional to the wavelength. So if we require the particular energy, we require the minimum amount of energy to occur the photoelectric effect. So it means we require the particular wavelength, or we require the wave of particular frequency. Then only the minimum required energy we can get. So you can, in other words, you can say you require a minimum frequency waves that is required to occur the photoelectric effect. So a minimum frequency of light required for the photoelectric effect to occur. So Einstein gave some explanation for this photoelectric effect, and here is the equation: half MeV square is equals to h nu minus phi. So half MeV square is equals to h nu minus phi. So this is phi is the minimum amount of energy. This h nu is the energy of photon we are having, and this is the kinetic energy of the leaving electron from the metal surface. Okay, so from this equation you can see that if h nu and phi are equal, means your incident wave on the metal surface is having same energy, having equal energy, that is minimum energy required, like h nu is equals to, like suppose phi is equals to h nu. Means suppose a particular metal requires some particular energy and your incident light is having same energy only. So it means that phi and h nu will be equal. So that means this half me v square will be 0. If this h nu is greater, if h nu is greater than phi, what is the meaning of it? It's meaning that h nu is the energy of the photon. So energy of the photon is greater than the minimum energy required for the photoelectric effect to occur. So it means that the photon are having more energy that is required. So it's mean this half MeV square will have some positive value because h nu is greater than phi. So half MeV square is having some positive value. So it means that the living electron will also have some kinetic energy. If h nu is less than phi, so this cannot have negative value. So that cannot be possible. Okay. So photoelectric effect will not occur because the energy of photon is less than the required minimum energy phi. Because if the impinging energy is not equal to phi, then there will be no photoelectric effect. So the explanation of photoelectric effect suggests two important points. It's very important points you can see here. The electromagnetic radiation of frequency mu cannot possess any arbitrary amount of energy. So it's very important that it cannot possess electromagnetic radiation of frequency nu cannot possess any arbitrary amount of energy. It can only possess energy like h nu, 2h nu, 3h nu, and h nu. So the energy of the photons, the energy of the electromagnetic radiation will only in this form, like nh nu, 1h nu, 2h nu, 3h nu. It cannot be 2.5 h nu, 3.5 h nu. So it will be particular integer only. It can only possess energies in h nu, 2h nu, 3h nu like form. Second one is electromagnetic radiation of frequency mu behaves as though it consists of 1, 2, 3 or n particles each with energy h nu. So again, we have considered that the light is having some photons, some imaginary particles called photons. So that will be in integer forms only. So electromagnetic radiation of frequency nu behaves as though it consists of 1, 2, 3 or n particles, each with energy h nu. So each particle, each photon is having h nu energy, and suppose 5 photons are impinging, so their energy will be 5 h nu. If 10 photons are impinging on the surface, so it will be 10 h nu. If 100, then 100 h nu. And you can say the value of h. So these particles of light came to be known as photons. And value of the h obtained by the Planck is 6.55 into 10 to the power minus 34 joule second. It's very important. It's in radiation in electromagnetic theory and quantum theory. The h value is very important. So the h value is obtained by the Planck. It obtained by the experimentally and some theoretical calculation. The value is 6.55 into 10 to the power minus 34 joule second. And the current accepted value, accepted value are 6.626 into 10 to the power minus 34 joule second. So these are very important values. And these values are taken from the reference and the very important scientific discovery in the science on the law of distribution of energy in the normal spectrum by Max Planck. 1901. So 1901, this paper is having this data, the value of h. Come to the next slide. So the relationship between the energy of the photon and the kinetic energy of the emitted photoelectron can be written as follows. So in simple words, we can write the energy of photon will be phi plus energy of electron. So photon energy is having h nu, phi h nu theoretical plus energy of electron, you can say kinetic energy of electron half me v square, where v is the velocity of that electron, okay, me is the mass of electron. So electron showing the kinetic energy of that electron, phi is the minimum threshold energy required for the metal surface. Okay, and E photon denotes the energy of the incident photon, which is equal to h nu. Okay, so the mass of electron is considered as 9.1 into 10 to the minus 31 kg. So from this equation, if you know the h nu for a particular metal, okay, and if we know the photon, then we can find the energy, the kinetic energy of the electron. Okay, and I have already told you that if phi is less than if the E photon is less than the phi, then there will be no photoelectric effect. If E photon is equals to phi, it means that energy of electron is zero value, and if E photon is greater than phi, then only E electron is having some positive value, and the electrons are having some kinetic energy with them. And this slide is showing some data regarding wavelength, frequency, energy in joule, and energy in electrovolt. So here we can see the long radio waves, AM, FM, microwaves, infrared, visible spectrum, UV, X-rays, and gamma. Please hold for 1 second. Let me check the charger of my laptop. Please, I'm sorry for that. Okay, so here we can see that the wavelength. We can see the wavelength in form of 1 e raised to about 0.8 and e raised to 0.5, 0.2 in wavelength in meter. Okay. Frequency in hertz, energy in joule, and energy in electrovolt. So this visible spectrum is very important. Okay, so it is lying between this range. You can say that 1.0 into e raised to power 14 to 1.0 into e raised to power 16. So this is the range, and similarly, the energy is also lying in this range, and the voltage also lying in this range, and this is the meter. So these are the range mentioned. Like visible spectrum wavelength is 1400 nanometer violet to 700 nanometer red, and the corresponding band gaps is 3.1 electrovolt to 1.8 electrovolt. The visible spectrum wavelength is 400 nanometer, and color is violet, to 700 nanometer, color is red, and corresponding band gaps is 3.1 electrovolt to 1.8 electrovolt. The conclusion from these slides is that the solar energy spectrum is consistent with black body radiations. So solar energy spectrum is consistent with the black body radiation. Visible spectrum, a very small fraction of electromagnetic radiation. So in this slide, we can see the fraction of visible spectrum. You can see, you can check the fraction, you can check the portion of long radio waves, you can check the portion of radio waves. Now check microwaves, infrared radiation, UV, X-rays. So we can check the portion, and it's very small for visible spectrum. Okay. And third is chlorophyll. The chlorophyll ideally suited for absorbing visible spectrum. The three conclusion that are solar energy spectrum is consistent with black body radiation, visible spectrum a very small fraction of electromagnetic radiation, and chlorophyll ideally suited for absorbing visible spectrum. So that's how the plant are producing oxygen. So let's start with some simple questions. So first question is the wavelength of the most intense part of the spectrum associated with a black body space with increase of temperature. So in this question, the question is asking that the wavelength of most intense part. So the suppose you are having a wavelength band, complete band. So the most intense part means the part where that particular where that temp for that temperature the radiance is the radiance is having its maximum value. Okay, so wavelength of the most intense part of a spectrum. Okay, a spectrum associated with the a black body space with increase of temperature. So if the temperature increase, the most intense part, what happen? Increase, decrease, first increase, then decrease, or first increase, then decrease. So we have seen in our previous slides that it decreases. Okay, as the temperature increases, the wavelength of the most intense part of the spectrum associated with the black body decreases. You can check in the slides. Yeah. So you can see here the wavelength for this 5000 Kelvin and wavelength for 4000 Kelvin. So as the temperature is increasing, wavelength, the lower axis is wavelength. So wavelength is shifting towards left side. Okay. So if you increase the temperature, means the wavelength will shifting left side. So wavelength is decreasing. So again, the correct answer for wavelength of the most intense part of the spectrum associated with the black body decreases with increase of temperature. So the correct answer will be decreases. Okay, because we have seen the graph for radiance intensity with the wavelength for black body temperatures. So that is like this. Okay. So the lower part is wavelength. So this is suppose T1, suppose T2. Here T1 is greater than T2. If T1 is more, it means the wavelength is less. T2 is less when wavelength is more. It will decrease. The next question is phase constant has helped in understanding the lower wavelength region of a spectral irradiance versus temperature plot at temperature T as well as. So we have covered a very important effect in our previous slides. Okay, and we have seen the value of some constant was very important there for particular wavelength regions. Okay, we have covered that E is equals to 5 plus E electron, and E was H nu, where H was some Planck's constant and nu was frequency. Okay, and this equation was describing the photoelectric effect. Okay, so from options you can see the option A is saying Planck's and electrochemical effect. So we have not covered any electrochemical. This option cannot correct. It will not. It's strike off. Option B is Boltzmann and photoelectric effect. We have covered the photoelectric effect, and this equation is representing that, but there was not mention of any Boltzmann's constant. Okay. Third one is Planck's and photoelectric effect. Yeah, we have covered the photoelectric effect, and in this, the Planck's constant is playing very important role. So this can be correct. Again, Boltzmann and electrochemical effect, it is not correct. So the correct option is option C. So option C is correct. Okay. So option C is correct. So Planck's and photoelectric effect. So this slide we have covered in our previous class. So just for a quick revision, the wavelength, how we measure the wavelength. So it's the distance between the two peaks, from peak to peak for a wave. Okay. So wavelength cycles are measured in nanometers from peak to peak. The shorter the wavelength, the more energy it has. So the shorter the wavelength, more energy it has. And blue light has more energy than red light. You can see in this graph. So the waveform of blue, waveform of red, and waveform of green. So you can see the distance between the blue light is less as compared to green and as compared to red. So the shorter the wavelength, so because the lambda is the distance between these peaks, so this is distance is less for, so lambda blue is less than lambda green is less than lambda red. So the energy of, so the lower the wavelength means more the energy. So it B will have more energy. EB is greater than EG is greater than ER. Okay, more the and sorry, this one is, yeah, lambda red. So this is having more wavelength, so less energy. So again, this is also we have covered in last class that showing some spectral irradiance curve with the wavelength. Okay, this is the electromagnetic spectrum, complete electromagnetic spectrum. This is given wavelengths. The blue lights we have already covered it. Just for the quick revision because it's also important. So this is the visible UV and it's infrared. So this was the energy budget covered in last class. Okay. So we are having some incoming energy, but due to the atmosphere, due to the clouds, due to the Earth's surface, okay, some of energy is reflecting, some of energy is absorbed. Okay. So greenhouse gases are also playing important role in it, but they are also playing harmful role in it. So we have covered all those aspects. Now, question number 3. The particle of light is known as space, and it can only possess energy h nu, space, and h nu. So recently, around 4 to 5 slides back, we have covered a photoelectric effect. In that, we have concluded the photoelectric effect by 2 statements, and I already mentioned that those statements are very important. Okay, so those are, yeah, here it is. This one and this one. So the electromagnetic radiation of frequency nu cannot possess any arbitrary amount of energy. It can only possess energy is in form of h nu, 2h nu, 3h nu, and nh nu. And electromagnetic radiation of frequency nu behave as though it consists of 1, 2, 3 or n particles, each with energy h nu. So based on this, we can easily solve this question. Let's come to the question. The particle of light is known as, so option 1 is photon, 2 h nu. So photon is correct because we know that particle of light which is having some energy is called photon. Then second is phonon. So phonon, yeah, we have not covered this, so it's not correct. Photon, yeah, it can also correct. Phonon, it's not correct. So option B and D are totally wrong because we know the particle of light is known as photon. Now we are having two choices. Photon are having in option A and D. Okay, so from these option one will be correct. Let's see. So For the particle of light is known as photon. Okay, it's photon, and it can only possess energy in h nu, like n h nu. So n h nu will be n is integer. So it can be h nu, 2h nu, 3h nu, 4h nu, like this only. Now check the option A and D. So in option A we are having 2h nu, and in option D we are having 2.5 h nu. So we have already seen that the energy only in proper integer form only. It cannot be decimal form like 2.5 h nu. So this option cannot be correct. This option also eliminated. This option eliminated. So correct option is photon and 2 h nu. So the particle of light is known as photon, and it can only possess energy h nu, 2h nu, and h nu. So the correct answer is photon and 2h nu. Option A. Again a question. The full solar energy spectrum is consistent with the space, and the visible region of this lies between space. So we have covered the electromagnetic spectrum. We have seen various ranges. We have seen various phenomena. Okay. So I have covered this type of phenomena. Okay. So this is UV, visible, infrared. So we have covered this radiance, and this is lambda. So we have covered this. So we can say that the full solar energy spectrum is consistent with the whole spectrum is concerned with black body. Okay, so we are having black body radiation, and the visible region of this lies between. So this is the visible region lies between UV and infrared. So check the options. The first option is black body radiation. It can be correct. And for visible region of this lies between radio waves and microwaves. No, it cannot correct, because we know the visible region lie between the UV and infrared region. This is not correct. Second is brown body radiation. No, because it's black body radiation. But the next option is ultraviolet and infrared. So it's correct. But the radiation part is not correct. Again, black body radiation, micro infrared radiation. So this is not correct. The fourth one is black body radiation and infrared and ultraviolet radiation region. Okay. So this option is correct, because the full solar energy spectrum is consistent with the black body radiation, and the visible region of this lies between the infrared and ultraviolet. So the option D is correct. Okay. Now let's come to some flat plate collector. Because we have covered the solar energy, we have seen the photoelectric effect, and we know that solar energy, if we manage to tap off the energy from the solar, okay, so it's a huge potential, because we know that in 1 hour only we are getting the amount of energy that is that is our annual world consumption. Okay, so solar energy we are getting in 1 hour is equal to the annual consumption of our world energy, which is around 500 exajoules. Okay, so uh, so we are having multiple devices, we are having multiple technologies to tap off the solar energy. So in this, now we will cover some basic technologies which we are using from quite a time. So the first one is flat plate collector. So it's a flat plate collector. So basically, as the name suggests, flat plate. So there will be a flat plate, and collector means it's collecting the solar radiation. Okay, so solar radiation is collecting on this flat plate, and with some mechanism, it will heat the cold water. Okay, so let's see. So a flat plate collector is a heat exchanger. So basically, it is a heat exchanger. Okay, so we are having some cold water, we are having solar radiation, so we are exchanging the heat. We are exchanging the heat with the solar radiation. So the cold water is a less temperature. We are exchanging the heat with solar radiation, so the temperature of the cold water will increase. So plate collector is a heat exchanger. It converts the radiant solar energy from the sun into heat energy using the well-known greenhouse effect. So we have already covered the greenhouse effect. Okay, because we know greenhouse effect, like when the solar radiation strike the earth surface, they reflect. But when they reflect, okay, they reflect, then they strike with the greenhouse gases, and again those gases will radiate. Uh, those gases will, like you can say, radiate the heat, uh, radiate the rays, and that will be infrared spectrum. And infrared, again they will do in this in a loop. Okay, so basically the heat that is coming to the earth's surface will left in a very less quantity if the greenhouse gas quantity is very high. So in that same way, you can see that we use a glass sheet or a glazing sheet. Okay, some other normally we use glass. So glass is transparent to the light, but it is opaque to the infrared spectrum. Okay, so solar radiation are in visible spectrum or UV spectrum. They are not in infrared spectrum. But when they reflect back from the surface, okay, so when they reflect back, they comes under infrared spectrum. But the glass is opaque to the infrared spectrum. So here you can see a setup. So this is the enclosure. You can see this enclosure. So you can see this enclosure, okay. In enclosure, you can see some tubes. Some tubes are extended, okay. This is a manifold, and one manifold will be here. One manifold will be here. One manifold is here, okay. So tubes are connected with these manifolds. And these tubes are placed on a base plate. You can see this is the base plate. This base plate. So tubes are connected to that base plate. And here is a manifold. So this manifold, the cold water is in, and the hot water is out. It's this includes a seal from the sides. Okay, at the bottom from the plate. Okay, the plate's bottom is insulated using foam or some aluminum insulation. Okay, so this is glass glazing sheet or glass sheet. So this setup, when put up in the open atmosphere, so the solar radiation will strike this glass plate or this glazing sheet. So this glazing sheet is will transmit the solar radiation because it is not opaque and will not reflect, because solar radiation are in shorter wavelength and more energy. So they will strike the glass and they will pass through the glass and they will strike the base plate. Okay, base plate can be made from some copper or some high conductivity material. Okay, the tubes are also made from copper, and those are aluminum, or those are attached with the base plate. Okay, and in these tubes water is flowing. Okay? So when the solar radiation is striking continuously, so after the striking the base plate, after striking the tubes, the reflected rays will be in infrared spectrum, but the glass is opaque to the infrared radiation, so that heat will be trapped inside this chamber. Okay, so you can see this is chamber. Okay, so there is some distance between the base plate tubes and the top glazing sheet. So in that sheet there is a vacuum, you can say airlock. You can say the some airlock is there. So that will trap trap the solar heat, because the reflected radiation are in infrared spectrum, and the glass is opaque to the infrared spectrum. So it will work like a greenhouse effect, and this will heat these tubes, and these tubes are a good conductor because they are made from good conductive material. So they will conduct that heat to the material that is inside, or to the fluid that is inside those tubes. So the cold water is flowing through these tubes. So the cold water will be heated. Okay. And you can see we get the hot water from this side if we supply the cold water through this side, because we know the when the water is heated, the density of water will be lower. So the hot water will rises up and cold water will remain down. In this way, the hot water will rises up, and you can from the top point you can get the hot water, and from the bottom point you have to supply the cold water. So this is a basic working of a flat plate collector, a very simple working. So it collects or captures solar energy and uses the energy to heat water in the home bathing, for bathing, washing, and heating, and can even be used to heat outdoor swimming pools and hot tubs. So there's a multiple use. I think you all have seen somewhere this flat plate collector, or maybe some of you are having this collector at your home or maybe at your hostels, and in hotels normally they are using it because it's saving it is direct saving the electricity. Okay, so yeah, it can be used. So this is the basic principle of flat plate collector. Now there is second version also. In this flat plate collector, there is no provision of storage. So directly we are putting cold water and we are getting hot water from other side, and there is no system of storage. So, but we can like do this like we can put a hot water storage tank at upside, and that tank is supplying the cold water, and from the same tank from the upper side we are having the hot water flow. Okay, so it's basically a thermosiphon. So basically, due to temperature difference, the cold water is having more density as compared to the hot water. So the hot water will move upwards as compared to the cold water due to lower density. So in this way, without any pump, without giving any energy, in natural way, using the basic convection and heat transfer, we can put the system for running. Okay, it's called thermosiphon. It's called thermosiphon hot water system. So this is a hot water tank, storage tank. You can see the blue part is cold water, and the red part is hot water. And you can see this pipe is supplying the hot water to the lower section, and the upper part is connected to the hot water. So from here you can get the hot water, and from here you again to supply the cold water. So due to the temperature difference, there will be density difference, and due to density difference, the hot water will be up as compared to the cold water. So this will again flow through this flat plate collector. So these are actually side view. So it's a perpendicular. So the long tubes. This is a manifold. Maybe they are attached at the end. In this way, it will observe the solar radiation, and you get the hot water. So the thermosiphon system is the most common type of solar heated hot water system. You have seen this type of systems at your home or in your hostel, which are having the complete system, hot water storage tank and the flat plate collector. In previous slide, we have only seen the flat plate collector, but now it's connected with the hot water storage tank. So now this is a complete system. It can be used in houses, it can be used in hotels, it can be used in hostels, and anywhere where we want some hot water without giving any energy. So the thermosiphon system is the most common type of solar heated hot water system on the market, and most commercially available passive direct solar hot water system use this type of roof mounted plate collector and storage tank combination. So for this, basically we require three, in the system there are three major components. One is the flat plate collector, second one is the hot water storage tank, and third one is the support structure. Okay, just give me 1 minute. Is anyone having any doubt? Let me know if anyone is having any doubt. Okay. Am I audible? Anyone? Is my slides visible? If anyone has joined, please respond. Is my slide visible? Are you able to see the pointer? Is my voice is coming smooth or having any disturbance? If there is any disturbance in my voice, is any disturbance in slides or any disturbance in the pointer or any disturbance in anything, please let me know. Okay. So anyone not responding, so I'm assuming that everything is fine. Let's continue. So in previous slides, we have covered plate collector. Now let's see some other type of collector. This system is having some limitation actually, because we are getting the solar radiation, but the temperature of the hot water will not go up to can go up to certain temperature only. Okay, because the solar radiation intensity we are not getting as required. Intensity is there, but we are not able to collect it more efficiently. So we have developed some other systems which can collect or which can point out more radiation at a particular point. So these are solar disk collector. Okay, so in left side you can see the diagram. There is some a curve structure. Okay, you can see this is a mounting structure and this is a curve structure. Okay, so these are some, you can see the some mirrors type or some lenses, some lens is there. So solar radiation is impinging on this, they are reflecting towards this receiver. Let's see how this works. So another type of concentrating solar collector that optically reflects and focuses the sun's incident solar energy onto a small receiving area using mirror or lenses is called a solar disk collector, or more technically a point focusing collector. So the points here which is need to be highlighted is another type of concentrating solar collector. Okay, so the concentrating solar collector means this system is concentrating the solar radiation to a particular point. Okay, so we are using some lenses, we are using some mirrors, and using those mirror lenses we are concentrating the solar radiation to a particular point, because if the radiation is distributed, then the effect of the heating will be less as compared to if you are concentrating the radiation. Okay, suppose you can you can understand using a simple example. Suppose you are having 100, you are having 10 plank of woods. Okay, so if you are burning all the planks together, then there will be more heat. Okay, and as compared to the burning those planks individually. Okay, if you are burning those planks individually at a certain distance, so you are not getting enough heat to cook your food. But if you put together those all 10 planks and you heat it together, so you can get enough heat for your cooking. In similar that way, using this solar disk collector, we are concentrating the solar radiation to a particular point, because at that particular point we require high temperature, and using flat plate collector we were not able to concentrate the solar radiation, so we have developed a system. So in this we are getting the solar radiation same, but now we are having some mechanism. Using those mechanism we are focusing the solar radiation to that particular point where we require the temperature. Okay, so the concentrating solar collector optically reflects and focuses. It's optically reflects and focuses the sun's incident solar energy onto a small receiving area. So this is the receiving area. Okay, this is, you can say, the glass or optically reflecting panels. So the sunlight is impinging on this, and this is reflecting to this a particular point only. It's focusing, all the reflection will point towards this. So suppose light is impinging here, it's again reflecting at this only. So basically it is located at a focus point. Okay, and this is, you can say, a parabola. So these all incident radiation is focusing at this particular point and it's collecting it. So at a particular point, at a small area, we are having more solar radiation. Okay, at small area we are having more impinging radiation. So in this way we can get more temperature. So in this way we can get up to 1000 degrees temperature. We can go up to 1000 degrees centigrade or even more if the collector is having more area. Okay, so depend on the area, it depend on the length, focal length, and all things. Okay, and how you are tracking the sun, because sun tracking is also important. So depend on other factors, you can go up to 1000 degrees temperature. The solar disk is formed into a paraboloidal shape by stamping them out from thin sheet metal or thin aluminum coated mylar, and which themselves can be anywhere between a few feet to several meters in diameter. So you can see the material is very thin metal sheets or aluminum coated mylar. Okay, and which themselves can be anywhere between a few feet to several meters in diameter. The parabolic disk collects the incoming solar energy directly from the sun and concentrates or focuses it on a small focal point area positioned in front of the dish. So this is the dish. Okay, so all lights is impinging on this dish and they are reflecting to a particular point only, this focus point. The parabolic disk collects the incoming solar energy directly from the sun and concentrate or focuses it on a small focal point. Small focal point will be your target area. So here you can put some, here you can put your water tubes in which you want to heat water or anything which you want to heat. So you can put it there and at this focus point. So all the impinging solar radiation on this solar dish will be concentrating on this particular point and you will get the required high temperature. So this is a simple diagram. You can see here. Okay, so basically this is similar. So these are solar radiation, they are impinging it here and directly going this side, again here, this side. So anywhere they striking the surface, they're reflecting to this particular point only. Okay, and this point will get more solar radiation. The temperature we are getting is higher as compared to the plate solar collector. Okay, so this is solar disk collector. Now let's come to the next slide. So this is parabolic turf reflector. So it's again a different method to do. So the parabolic turf reflector is a solar thermal energy collector designed to capture the sun direct solar radiation over a large surface area and focus. So in solar disk collector, the surface area was small, but in this case, parabolic turf reflector, we are having a large surface area and focus, or more generally, concentrated onto a small focal point area, increasing solar energy received by the more than a factor of 2, which means overall heat per square meter of turf. Okay, so we are getting, like, we are increasing the radiation up to twice. Okay, so we are getting the twice the energy if we get in simple form. The parabolic trough reflector is solar thermal energy collector designed to capture the sun's direct solar radiation over a large surface area and focus, or more generally concentrate it onto a small focal point area, increasing the solar energy received by the more than a factor of 2, which means overall heat per square meter of trough. Okay, the shape of the concentrating solar collector must be specifically designed so that all the incoming sunlight reflects off the surface of the collector and arrives at the same focal point, no matter what part of collector the sunlight hits first. So you can see this is again in a parabolic form. At the center, we are having some tubes. So they are again the sunlight is reflecting, striking this surface and going here, reflecting, going here, reflecting, going here, reflecting, going here. So again, we are focusing. We are having a large area. The sunlight is impinging on that area, and we have designed. We are having a curvature. So based on the curvature, all the impinging radiation are reflecting to that particular focal point only. The shape of the concentrating solar collector must be specifically designed so that all the incoming sunlight reflects off the surface of the collector and arrives at same focal point, no matter what part of the collector the sunlight hits first. Okay. Concentrating solar collectors for residential application are usually a U-shaped parabolic trough, hence their name. The concentrator the sun's energy on the absorber heat tube called a receiver that is positioned along the focal point axis of the reflective trough. So there is a receiver. Okay, this is the collector, solar energy collector, and this is the receiver. So next slide we will look at more clearly. Yeah, here in this diagram you can see. So first of all, this is a central heat pipe. Okay, so this is a heat pipe. It is having, it's located in central at a focus point of this curvature. We are having curvature at the focus of this curvature, focal end of this curvature. We are having a central heat pipe. So in this heat pipe, we are having fluid in at left end, and at the right end, fluid out is there. Okay. So this is a parabolic shaped reflective trough, and there's a reflective coating or mirrors. We can do some coatings that will reflect the sunlight. Okay. Or we can also use the mirrors. This is the rotational axis to rotate this so that the solar radiation strike it perpendicularly, and more or it can track the sun. Okay, suppose if you are not doing the tracking, and suppose sun is on this side, and uh, this is looking at this side. Okay, so it will observe very less radiation. Okay, the intensity of radiation will be less, so it will try to track the sun. So again, it will again. So we put it like it always face the sun. As you can see in this diagram, the rays are directly coming on this, and they are striking the parabolic surface and they're reflecting to the central heat pipe, and the fluid is in and out. It's heated in between. Okay, and we have to do some supports also, because this is structure, it requires support also. This is north and south, so it is east and west. Okay, so basically this is traveling the so this is west and this is east. This is west. So sun is going from east to west. Okay, so we can rotate. We can rotate the rotational axis in east west. Okay, so it will focus the sun always and try to get maximum solar radiation collection. This is typically a reflector design. Now let's see some questions. So the question number 5 is, the flat plate collector to harness solar energy require space conducting sheet made of space material. So we have covered the flat plate collector. In flat plate collector, we have seen we are harnessing the solar energy using some conducting sheet. Okay, which are conducting sheet made of which material? So ceramic, it cannot be. Yeah, metal, because metal is generalized, so metal can be. Copper can be. So option A is wrong. The correct options will be from B, C, or D, because metal is a, this is not specifying any particular metal, because we require some conductive metal. So copper is also conductive, aluminum is also conductive. So where there are different various metals, those are conductive. Okay, silver is also conductive. So so metal is basically a group, so it can be correct. So we require electrically or thermally or magnetically. So we are collecting the thermal heat. We are capturing the thermal heat. We are not doing any electrical activity. We are not having any magnetic properties. Okay. So we are only considering the heat energy. We are tapping off the solar energy to heat the cold water to hot water. So we are basically working on heat exchangers. Okay, we are transferring the heat from high temperature to lower temperature. So basically thermal energy is included here. Okay, so the flat plate collector to harness solar energy requires thermally conducting sheet. Basically thermally conducting sheet made of, so option B and C are having thermally and metal and copper. So both options are correct. Option B and C are correct. Because when we are using the flat plate collector, understand the main point. We are just transferring the heat energy of solar radiation to the some fluid, or you can say water. You are using that energy to heat the water. Okay, so basically you are increasing the temperature. You are providing the heat energy. So there is a thermal conducting sheet is required. Okay, and it can be of any metal or copper. So option B and C are correct. Sorry. Now question number 6. So metal sheet in solar energy collector is coated with black color too. Now we are having three options. Option 1 is reduce the reflection of sunlight. Option 2 is, statement 2 is increase the absorption of sunlight. Third is protect from the environment. So we know that black color, it absorbs all solar radiation. It behaves as a black body. It will absorb all solar radiation. So increase the absorption of sunlight. So this is correct. Because if you have painted the black, mean you are getting the more and more energy, you are not reflecting. Okay. So you are absorbing more energy. So increase the absorption of sunlight. Now reduce the reflection of sunlight. Yeah, because if you are absorbing more, mean very less reflection. This is also correct. Protect from the environment. So we are not, we have covered many slides. We have covered the various aspects of the solar radiation, and we have also seen solar radiation spectrum, black body spectrum also. But there were no, there were no space in which we have covered this, we are using the black color to protect from the environment. This option is incorrect. So the correct statements are statement 1 and 2. Now let's check the option. Option A is only 1. Yeah, 1 is correct. Option B is only 2. 2 is also correct, but not only. Okay, because both statements are correct. So this option cannot be correct. This option cannot be correct. Now come to third one. Both 1 and 2. It means option statement 1 and 2 both correct. So this option is correct. Now 1 and 3, because 3 is not correct, so this is also wrong. So the correct option is option C. Both 1 and 2. Because metal sheet in solar energy collector is coated with black color to reduce the reflection of sunlight, so it will absorb more and more sunlight, okay, and increase the absorption of sunlight. Option 7. Now let's come to the question number 7. Glass plate on a solar energy collector setup. Blank. We are having 3 statements. So glass plate on solar energy collector. So recently we have covered this. So in this flat plate collector, we have seen there we are having some tubes. Okay, we are having some glass plates, and I have already mentioned that a flat plate collector is a heat exchanger that converts the radiant solar energy from the sun into heat energy using well-known greenhouse effect. Okay, so basically the glass plate is what it is doing. So the glass plate is basically transparent for the solar radiation, but it is opaque to the infrared radiation. So it's just trapping the solar heat inside that particular chamber, and that heat is heating the absorbing tubes. Okay, absorbing riser tubes in which the fluid is flowing. So basically, the glass is working as an opaque for the infrared radiation and trapping the heat. Now let's see the options. What options we are having? Okay, so the glass plate on a solar energy collector setup keeps the visible radiation stuck between metal sheet and glass. Okay, reduce convective losses, reduce infrared radiative losses. So option 1 is keeps the visible radiation. So is it correct? Because we know that visible radiation spectrum, when solar radiation strike the surface, any surface, and reflect back, they will not remain visible radiation because they will lose the energy and they will come under the infrared spectrum. Okay, so they will not come under the visible radiation. Okay, so this option cannot be correct because it will not in visible red, it will be in infrared radiation. So glass plate on solar energy collector setup don't keep the visible radiation stuck between the metal sheet and glass. It keep the infrared. It keep the infrared radiation stuck between the metal and sheet. So this option is incorrect because it is saying the visible radiation, but in actual it will be infrared. Okay. The second one is reduce convective losses. So yes, because the glass is behaving as an insulation. Okay, it is eliminating the contact. So this was the enclosure. So your tubes are there. This is the glass. Okay, so water is flowing through these tubes. So this only particular enclosure only. Okay. So outside the air convection, the free convection is there, but this glass is acting as an insulation. Okay. So it reduces the convective losses, reduce infrared radiative losses, because infrared radiation also radiates some heat, radiates some energy, but it's opaque. The glass is opaque to the infrared radiation, so it reduces the infrared radiative losses. So option 3 is correct. Option 3 is correct. Option 2 is correct. Now let's see the options. So first one is both 1 and 2 correct. Yeah, it cannot be correct because statement 1 is wrong. This is wrong. Now all 1, 2 and 3 again it cannot be because statement 1 is wrong. Both 1 and 3 again it cannot be true correct because statement 1 is wrong. The correct option is both 2 and statement 3 because it reduced the convective losses because the glass act as an insulation between the outside air and the tubes inside this closed box, or you can say the closed enclosure. So it reduced the convective losses, and the last one is it reduced the infrared radiative losses because the glass is opaque to the infrared radiation. So the correct answer, the accepted answer is both statement 2 and statement 3. The correct option is option B. Now question number 8. So we are having again a statement. The ability to pick up heat is limited by the area of a flat plate collector exposed to sun. Okay. It can be increased by replacing the tube by fins or a mesh. So the ability to pick up heat is limited by the area of flat plate collector exposed to the sun. So basically it's saying that how much of heat will a flat plate collector will pick up? It depends on the exposed area. So as large area of solar plate collector you are having, as more heat you will pick up. So it can be increased by replacing the tubes or by fin or a mesh. If you replace this by some tubes, by fins or mesh. In this we are having some tubes, okay? But now instead of tubes are having circular cross section. Tubes are having circular cross section. Now if we replace these by fins or mesh, so the heat pickup will increase or not. Let's see. The reasons are fins and meshes have more surface area than tube, and fin increase more air resistance. So statement 1 is correct because as you compare to a tube to a fin, a rectangular fin, you will see the rectangular fin is having more area as compared to this tube. Okay. And if you are having a particular fins and mesh have more surface area, so yeah, statement 1 is correct. Fins and mesh have more surface area than tube. Now come to the statement 2. Fins increase more air resistance. So is there anything about air resistance? Is there we are having some convection between the tubes and the air? Yeah, so basically no, because the fins, the tubes or anything will be covered in a enclosure, because solar flat plate collector we are having an enclosure, and that enclosure is having some tubes or fins, and there is no direct contact of air with those tubes or those collecting surfaces. Okay, those are collecting the solar radiation. There is no direct contact. In this way, fin cannot increase more air resistance because at the inside there is no moving air, there is no flowing air. So basically, it's not there. So fins increase more air resistance is a false statement. So reason 2 is incorrect. Reason 1 is correct. So let's see the options. Only reason 1 follows. Yeah, correct. It's follow because option 2 is sorry. The statement reason 2 is incorrect. So the correct option will be only reason 1 follows. Only reason 2 follows, it wrong. Both reason 1 and 2 follow, again it is wrong because reason 2 is wrong. Neither reason 1 nor reason 2 follow, it is wrong because 1 is correct. The correct option is option A. Let's come to the correct option is option A. So here you can understand the better, okay? So you can see here. So these are the fins, okay? So you can see, compare surface area. So the surface area of fins will be more as compared to tubes only. Okay. So these are having more surface area and these are enclosed in an enclosure. So there is no direct contact of air. So statement 2, like fins increase more air resistance, will be wrong. Give me 1 minute, just I'm having some water. Is anyone having any doubt? You can ask. Am I audible? Okay. If anyone is having any doubt, you can ask. Actually, it's interactive session. If you want to ask something, you can ask. Question number 9. So now a parabolic disc reflector are in the shape of a space mirror, which uses the idea of concentrating solar energy at space focal point. These are made up of highly polished stainless steel or aluminum surface. So we have mentioned in our solar disk collector slides that we can use some mirrors or some shining sheets, okay, or some other material that can reflect the solar radiation effectively. So if we are using mirror, then what kind of mirror it should be? It should be convex or concave, and which use the idea of concentrating solar energy at a focal point. So the options are single or multiple. So are we having single focal point or multiple focal point? Or are we concentrating the energy at a particular point or some different points? So as we have already seen that in that part we were having like this structure, okay? and the solar energy was reflecting like this only. So basically, at this point, at focal point, you are having your receiver, and these surface or having a mirror is reflecting the incident solar radiation to this particular point only. So the shape of this mirror, if you are using mirror, then this should be concave mirror. Okay, so it will focus the light on a particular focal point. So the correct option will be concave mirror, which uses the idea of concentrating solar energy at a single focal point, because we are focusing all the energy to a single focal point only. So the parabolic disc reflector are in the shape of a convex mirror, which uses the idea of concentrating solar energy at a single focal point. These are made up of highly polished stainless steel or aluminum tubes. So correct option will be concave and single. These are incorrect, because multiple is not correct, and we are using concave mirror. So option B will be correct. So correct option is option B. And see, the correct option is concave and single. Again, you can see here with this example, with this figure, that this is the main focal point that we are having receiver our, and these are solar radiation. They all are incident on the surface. This is having concave shape. And they are again all concentrating at this particular point only. So number 10, a single focal point parabolic disc collector is said to be. So a single focal point parabolic disc collector is said to be. So a flat plate collector. So no, in flat plate collector there is no single focal point. So from directly we can eliminate through the options. So the first option cannot be correct, because in flat plate collector we are having some enclosure in which some tubes are there, some flat plate is there, some glass is there. So we are not focusing, or we are not concentrating the solar radiation to a particular focal point. So it cannot be correct. Non-imaging concentrator, no, because in not non-imaging it's no. Turf collector, because in turf collector we have seen that there's a large surface. Okay, we are using in a particular tube, not a particular point actually. We are using like this structure. Okay, so that is focusing on a particular big area, not a particular point. It can also not correct. This is not correct. So remain of imaging concentrator. So yes, a single focal point parabolic disc collector is said to be imaging concentrator. Okay. So basically it create a virtual image. Suppose it will, like in previous slide, you can see that this is sun. This is reflecting the rays to this particular area, and it all reflect at this point. So this will create a image of the sun at this particular focal point. That's why it is called imaging concentrator. Okay, so the temperature at this point will be very high. Okay, like the temperature of the sun, which is very high. So basically, it's imaging concentrator. The correct option is option D. A single focal point parabolic disc collector is said to be imaging concentrator. So the correct option is imaging concentrator. Okay, now we are having some sample true and false. So I would like to invite you all to participate in these questions. Okay, so if we interact, it will be very good session actually. Let's start. A black body absorb radiation incident on it. True or false? Anyone want to answer? Please answer. A black body absorb radiation incident on it. Is this statement true or false? In our initial slides, we have learned about black body. I will give you 1 minute to answer. If anyone want to answer, please. Okay. So we have already covered that black body absorb all radiation. Okay. And Kirchhoff's made a small hole in a particular enclosure, and that enclosure was totally insulated. And when you are pointing some light on that particular enclosure, so you will not get any reflection. So you are not getting any image from that, because there is no chance that the light that is going inside will come out again. Okay, because the black body absorb radiation inside incident on it. Okay, it's true. So basically, a black body absorb radiation incident on it. It's a true statement. So it is true. Now come to option 2. Solar concentrators can help raise the temperature of water above 100 degree. Solar concentrator can help raise the temperature of water up above 100 degree, because in flat plate collector we were having some limitation, and due to those limitation we were not able to increase the water temperature up to a certain point, you can say up to 80 degree or 90 degree, because it was, you can say, there because solar radiation is, you can say, discrete, or they were not focusing on a particular point, they were spread out in a particular area. Okay, so what we changed in solar concentrator, what is the change of technology we applied in solar concentrator, and what were happening, we have already discussed that, and the name is resting concentrator. So basically we are concentrating the solar radiation to a particular point. So is it able to increase the temperature above 100 degree using solar concentrator? Is it true or false? In our previous slides, we have covered it. Anyone want to answer? Please answer. I'm giving you 1 minute to answer. Okay, let me again repeat the question. The question is that solar concentrator can help raise the temperature of water above 100 degree. Is it true or false? Can we increase the temperature of water beyond 100 degree if we concentrate the solar radiation to a particular point, as we see in solar disk collector, where we are using concave mirrors? and at a focal point we are putting some water, suppose. So the all radiation will be concentrating at the particular focal point. So yes, option 2 is true, because as I already covered, if we are using the solar concentrator, we can focus the all radiation to a particular point only. Okay. So all radiation can be focused on a particular point. So yes, this is correct. The correct option is true. Solar concentrator can help raise the temperature of water above 100 degrees. Option 3. A parabolic disk concentrator typically does not need tracking because it is curved in all directions. Is it true or false? Do you need tracking of the parabolic disk connector? And what is the meaning of tracking? Tracking means that your particular concentrator, your particular collector is tracking the sun. Okay, because in whole day Earth is moving, Earth is rotating. Okay, so basically the position of sun with respective to our location is changing with that particular location. Okay, so do we need to track the sun to get the maximum solar light, to make the maximum solar radiation? Do we need to track? So I'm giving you again 1 minute, and let me repeat the question. A parabolic disk connector typically does not need tracking because it is curved in all directions. Anyone? Suppose you are not tracking the sun, you are facing, suppose in west, your concentrator is facing in west direction, sun is in east direction. So is it collect all the radiation, or is collecting more radiation or not? Basically, no. We have to track. Okay. Sun tracking is very important in parabolic disk concentrator. Otherwise, it will not absorb, it will not reflect the maximum intensity of radiation to the concentrator. Okay, so it's true or it's false, because the parabolic disk connector requires tracking. It requires. So parabolic disk concentrator parabolic disk concentrator requires tracking because it is curved in all directions. A glass plate is used on top of the flat plate collector in order to A glass plate is used on top of the flat plate collector in order to prevent infrared radiation from coming in. So we have covered the flat plate collector. In that, I have already explained the role of the glass, as glass is working as the same effect that the greenhouse gases are doing for our atmosphere. Okay, in that similar way, the glass is increasing the temperature inside those tubes, and it's used to trap the heat between the enclosure. So is it true or false? I'm again giving you 1 minute to answer this question. The question is that, I'm repeating this again. Question number 4. A glass plate is used on top of the flat plate collector in order to prevent infrared radiation from coming in. So first of all, think when we are having a solar flat plate collector, which radiation are going inside that particular glass and which radiation are coming out. Think in that perspective. After that, you can easily answer this question. I'm giving you the hint also. We have covered various electromagnetic spectrum for the black body radiation, in which the some important are UV, visible, and infrared. So I think you can take some hint from this statement, my statement. Three important spectrum are UV, visible, and infrared. So I have already mentioned that glass is transparent for a particular spectrum, and glass is opaque for a particular spectrum. So based on that, you can answer the question number 4, which is a glass plate is used on top of the flat plate collector in order to prevent infrared radiation from coming in. Anyone? So first of all, infrared radiation is not coming in, okay, because the light is in visible range, or you can say in the, or maybe some part in UV range. So that is striking on the flat plate collector, and after the striking, okay, the glass is transparent to those ranges, and after they strike the collector plate, the reflected radiation will be in infrared radiation. That will be trapped because the glass is opaque to the infrared radiation. So this statement is false because a glass plate is used on top of the flat plate collector in order to prevent infrared radiation from coming. It is false. Now question number 5. Humans and animals give out infrared radiation. Humans and animals give out infrared radiation. Is it true or false? I'm giving you 1 minute to answer this. Anyone want to answer, please? Okay. So the human and animals give out infrared radiation. Yeah, it's true because our body is also having some particular temperature. Every temperature is having some radiation associated with that. Maybe the intensity of radiation is depend on the temperature. As high as the temperature means the intensity of radiation is more, but we are giving out some radiation. So this statement is correct. So humans and animals give out infrared radiation. So these are the answer: true, true, false, false, and true. Now again, I can suppose if we want to, we won't require temperature in a very high rate, okay, or very high range. We require more and more heat, so uh, we can put a large park like this, okay. In this park, we can build a tower. At a tower, we put a receiver, and in surrounding area, we put different type of, we put, you can say, at different angles, some mirrors, or some, you can say, surfaces that can reflect the incident solar radiation. They're putting it so that this all mirrors will reflect the rays directly to a particular point only. So in this way, suppose this is side view. Maybe this row containing hundreds of mirrors. This row containing hundreds of mirrors. This row containing hundreds of mirror. Again, this row containing 100. This row 100. In this way, we can build a large park in which we can capture the solar energy, and we can concentrate the solar energy to a particular receiver using the angles. Okay, in this way, we can get thousands of degree temperature at this receiver. This is also, like you can say, an example of solar disc collector. But here we are not using a one single disc collector. We are having multiple disc collectors at different angles. So all they are all reflecting the radiation to a particular point only. Okay. So we are having 5 minutes left. Anyone is having any doubt regarding today's class? Let me know. Let me quickly revise the slides. So if you are having any doubt regarding any slide, so let me know. In this we have covered the black body, about black body, okay? Black body radiations, what is it, and some basics of black body. In this we have discussed about Kirchhoff's law and what is the important points of black body radiation. In this we have seen the different wavelengths for UV, visible and infrared. Again, in this we have covered photoelectric effects. Same photoelectric effect. If anyone has any doubt, please let me know. So, okay, thank you everyone for joining this live session. So I hope you all understand the basics of week 4, and we have covered some sample assignment questions, and I hope these questions will help you in your current assignment, and you will be able to score maximum marks in the current assignment. Okay. So I am again saying that this recording and the slides will be shared to you by the NPTEL team. So don't worry if you are not able to attend this, you will get the link, and please try to attend it and try to participate in, because these are interactive live sessions. So you can ask any doubt in these sessions. So okay, thank you everyone for joining, and we will again meet on next Monday 6 to 8, and we will cover week 5 content. Okay everyone, I'm stop sharing. I'm okay. Okay, thank you everyone for joining. I'm ending the meeting. Thank you.